We introduce speculative inference on multimodal data streams. There is growing evidence that multimodal inference is more effective than using a single modality in applications such as speech recognition, health monitoring, and activity recognition. Just as we can observe a single scene from different vantage points, multimodal, multi-device sensing allows us to extract various properties about a physical scene. We can leverage these properties to independently cross-check information from alternate sensors, which is particularly useful in complex environments. One overarching challenge is how to process the distributed multimodal sensor data. Edge devices are capable of producing large and continuous data streams. The underlying assumption in existing models is that data from different modalities will arrive at roughly the same time. However, in the context of distributed multimodal models, data generation rates can vary widely across these data-rich sensor modalities. And due to network dynamics, bandwidth can fluctuate rapidly within a short period of time. So one data stream may arrive much earlier than another. For example, a video stream requires several orders of magnitude more bandwidth than an audio stream. So a cloud-based model may receive full data from an audio stream, but only partial data from a video stream. We currently have limited options to deal with such a scenario. One option is to block the inference pipeline and wait for all inputs to be available. However, this naive blocking method introduces end-to-end inference latency. Our experimental results show that it can lead to tens of seconds of inference latency in multimodal event detection, which is not acceptable for many real-time applications. Another option is to ignore the delay and force output by running inference over a subset of the sensor data. But this approach sacrifices accuracy and robustness. In our experiments, accuracy drops up to 35% can be seen, leading to erroneous decisions and poor user experience. To address this challenge, we introduce speculative inference on multimodal data streams to adapt to constrained bandwidth and unpredictable network dynamics. The notion of speculative inference is inspired by speculative execution in modern processors, which is highly effective at improving performance when different processes operate at different speeds. Just as a modern processor can speculatively execute instructions while waiting for data to arrive from slower physical memory, a multimodal inference pipeline does not need to wait for a slower stream's data to arrive. It can use the faster stream's data together with partially received data from the slow stream to impute features of the slower stream's data. Then the cloud can speculatively execute the inference pipeline using the predicted values. As with speculative execution, the remote computation engine needs to confirm the accuracy of the prediction. When inference results are determined to be insufficiently accurate, our system rolls back the speculative inference and updates the model's output. To implement such a system, we face several challenges. The first challenge is the design of an imputation method that is broadly applicable across different sensor modalities with different data sizes, inference tasks, and unpredictable delays arising from dynamic network conditions. The imputation module must also be lightweight because the practical deployment can be on resource-constrained clouds. The second challenge is that speculative inference should not make assumptions about the availability of accurate and synchronized timestamps from different devices, and should operate effectively despite time synchronization errors. IoT devices are generally not tightly synchronized with a global clock, and timestamps on such devices may not be accurate due to clock drift or sensor failure. Since IoT devices are often battery-powered, many devices may not implement synchronization at all. The third challenge is the design of the rollback method. Unlike traditional speculative execution in modern processors, there is no straightforward way to confirm whether the speculative inference is correct or not. The naive way to check whether the speculation is accurate is to re-execute the inference when more data has arrived, but this is clearly impractical. So we need to find a computationally efficient manner to roll back the speculative inference. We designed 3 modules to tackle these challenges. First, we proposed the use of a conditional generative adversarial network, or GAN, to predict missing or delayed input data from one modality. In general, a GAN trains 2 separate neural networks simultaneously: a generator that learns to map from a latent space to a data distribution of interest, and a discriminator that learns to distinguish between real samples and synthetic samples from the generator. It is a very effective upsampling approach to predict missing data. However, directly applying the GAN in our system does not work well due to differences in data sizes and underlying sensing modalities. For example, a raw audio stream is a 2D vector and contains only temporal information, whereas raw video is a 3D vector and contains both temporal and spatial information. Noise distributions are also different due to inherent differences between the sensors and their respective noise sources. Our solution is to impute missing or incomplete data by generating intermediate feature maps instead of generating raw sensor data. The diagram shows a typical audiovisual multimodal model. The model takes raw sensor data as inputs and computes intermediate feature maps f-slow and f-fast. The fusion layer concatenates f-slow and f-fast to generate an intermediate feature map f-concat. Finally, the learning layers use f-concat to compute the final output. To accomplish this, we reuse the multimodal prediction models in our data imputation module. Specifically, we use the intermediate feature map f-slow prior to the fusion layer as the input of the discriminator. The first learning layers often act as a feature extraction and denoising module in multimodal models, so f-slow has a higher signal-to-noise ratio than the raw sensor data. We then use the feature map f-concat after the fusion layer as the input of the generator to better utilize the correlated cross-model information. To adapt to dynamic network conditions, we configure various delay settings to train the GAN. Based on our experiments, the training overhead is only 8 to 20 hours, significantly lower than retraining the entire multimodal model. To tackle the challenge of synchronization inaccuracy on IoT devices, we designed a data alignment module without using timestamps or injecting synchronization pulses. The key idea is to reuse the data imputation module to generate 2 sets of feature maps: a feature map f1, generated by audio-only data, and a series of feature maps f2, generated by both audio and video data with multiple delay configurations. We observe that when the delay configuration matches true delay, these 2 feature maps are close to each other. So we search for the minimum L1 loss of the 2 feature maps among all possible delay configurations to find the best alignment. The figure shows an example. When 2 data streams are not well aligned, the intermediate feature map tends to be erroneous, which increases the L1 distance between the 2 maps. When the delay configuration matches the true delay, the 2 maps are close to each other, leading to a minimum L1 distance. We have described how the system computes speculative inference using incomplete data and how to align multiple data streams without using timestamps. But how can the speculative inference module ensure that its output is suitable for downstream processing, and when should it decide to roll back and wait for more data? Our design is inspired by a simple observation. Some prediction classes are resilient to incomplete data in one sensor modality, whereas others are more sensitive to incomplete data. For example, based on the complexity of lip movement, an audiovisual lip reading model can recognize the word under with less visual data than is required for the word allegations. To validate this observation, we conduct an experiment using 2 public datasets. The figures show the CDF of the minimum data requirements to achieve the best accuracy. We can see that in about 50% of the inference classes, the speculative inference can achieve the best accuracy with less than half of the full video data. This validates our observation that most classes are robust to speculative inference over low-fidelity data. For these inference classes, if the cloud has already received half of the full data in a prediction window, the system can proceed to output the result of the speculative inference. However, we can see that for less than 10% of inference classes, the cloud needs to receive over 90% of full data to achieve the best accuracy. For these inference classes, if the cloud receives less than 90% of the total video frames, the system will discard the speculative inference and wait for additional data. Then the rollback module will recompute and output the inference. The rollback module assumes that the distribution of the testing data is similar to the distribution of the training data. However, we observe that if limited training data is available, this assumption may not hold. In this case, the rollback module may need to be periodically updated as more data becomes available. Let's look at some key results. We implement the system in 3 multimodal application scenarios, including speech recognition, event detection, and activity recognition. Each dataset contains at least 2 sensor modalities, for example, audio and video, or accelerometer and gyroscope. In this presentation, we focus on experimental results using the second dataset. To demonstrate our system's ability to adapt to asymmetric bandwidths across modalities, we vary bandwidths to simulate fluctuating network conditions using both synthetic network traces generated with the Pensive library and real-world traces generated with Nexus 5 phones. The throughput is in the range of 100 to 1000 kilobits per second. Then we compare our system with 6 baselines. The first baseline is naive blocking, which simply blocks until all inputs from all data streams have arrived. The second baseline is adaptive bitrate streaming. We then compare our system against 3 existing video analytics methods. One is based on frame sampling, and the other 2 are profiling methods. Frame sampling minimizes the bandwidth required to transmit data by filtering out redundant information. Profiling optimizes video streaming configurations to minimize the inference latency while achieving the desired accuracy. Finally, we compare our system with an approach that retrains the multimodal model itself. This figure shows end-to-end improvement. We can see that adaptive bitrate streaming, frame sampling, and the retrained model achieve the minimum end-to-end latency, but at significant accuracy loss. Also, the training overhead of the retrained model method is about 10 times higher than our system, as our system only imputes intermediate features rather than the raw sensor data, and it does not need to modify the existing inference model. Our system shows comparable accuracy to profiling methods, but offers a latency speedup of at least 7 times. Finally, our system has about 2% lower accuracy than naive blocking, but achieves a latency speedup of 120 times. We also looked at the impact of individual modules, training overhead, IoT nodes, and more. Please refer to the paper for additional details. To conclude, we present speculative inference on multimodal data streams to adapt to asymmetric bandwidth. The system enables speculative execution of these models without waiting for all inputs to be completely available. We implement the system in 3 multimodal scenarios. Overall, the system achieves a latency speedup of 7 to 128 times, with the same accuracy as 6 baselines. Thank you for listening. We're happy to take any questions.